So when talking about energy, we do have to get the vocabulary clear. And so that's what I want to spend the next few example slides talking about. There's going to be 3 forms of energy that we officially define in this class that'll stick with us all the way to the end of Physics 2. It's really interesting when we get to energy considerations, especially later in the course or even later in the book about light and the types of energy that show up in those contexts. But for now, we're doing the simple examples, for the most part, of moving objects and how their energy changes when subject to sort of mechanical forces. Another remark is just about every problem we've done up to this point, we can reframe in context of energy, actually. Even those difficult problems with the 2 blocks and the pulleys and the ropes and all those things, those can still be formulated with energy. So let's go ahead and officially define the parts of energy. So the first one is kinetic energy. That's energy of motion. Okay, so anything that's moving has energy. A couple of things to be aware of is that, well, if motion is relative, does that mean energy is relative? Yes and no. We're not going to get into the subtleties about different reference frames when it comes to kinetic energy. You never do, actually. But yeah, so energy associated with an object's motion is kinetic energy. Even energy associated with an object's rotation is a type of kinetic energy. Because if you think about an object rotating, even a simple particle rotating in a circle, it has a tangential velocity. And so it's kinetic energy, which, if they haven't defined it here, let's just call it for what it is and just give the definition for kinetic energy at the risk of cluttering the conceptual conversation. Switch markers. So we define the kinetic energy associated with an object's motion to be 1/2 the mass times the velocity squared, technically the dot product squared, but we ignore that. And what are these units? It's kilogram meters squared per second squared, and we define that to be a joule. Book certainly talks about this later, but this is a kilogram meters squared per second squared. All right. Okay, and so that is the energy associated with an object's motion. It's pretty obvious. What about the next one? What about potential energy? So this is an energy associated with an object's position. And I want to kind of elaborate on that, because what do we mean by position? Because an object in deep space doesn't have a potential energy. Deep space means, far enough away from the gravitational pull of any big star, planet, or asteroid, or whatever. So what do we mean by energy of position? So it's not that position itself gives an object a potential energy. It's that an object's position near another relevant object is what gives it a potential energy. So I'll give you an example. I mean, everything located near the surface of the Earth has a potential energy, because every location in space around that Earth or around some massive object has what's called a gravitational field around it. And we're certainly not going to get into the idea of a gravitational field, but every location has a strength of gravitational field. And then if you bring a massive object at that location, then now it has an energy. So these objects acquire a potential energy by being near an object of relevance. But we're not talking about potential energy in its strictly narrow sense of just like MGH or near the surface of the Earth. It'll be a different formula for potential energy for planetary motion, celestial motion. There's a different formula for potential energy for stretchy objects. Anything that's stretchy has potential energy associated with it, because if you imagine like either like a bouncing trampoline, or if you imagine like a rubber band stretching a rubber band, there's potential energy associated with that stretching or compressing. And then finally in Physics 2, especially in times of the year when it's very dry, you can certainly feel this a lot more than other times, that the potential energy is associated with the presence of electric charge near you, right? You get the feeling of your hair standing on end when you're next to an object that's charged. So that's going to be the context of potential energy in its broader sense. And it's even broader than that, but we'll stick with that for now. Now, what about thermal energy? That's the third one. Thermal energy is the microscopic sum of all of the potential and kinetic energies of the elements of the solid or the liquid or the gas or whatever the specific object you're dealing with. So this is not something that you calculate on a day-to-day basis, but you kind of do, because it's related to an object's temperature. And if you can measure the temperature of an object and you know how much stuff is in that object, then you can measure the thermal energy. Yeah. In fact, you don't even need to know the amount of stuff in the object. Well, technically you do. Yeah, you need to know either the number of moles of the object or the number of particles that make up the object to get the energy from the temperature. But they're related, and we'll explore that relationship much more in the unit on thermodynamics near the end of the semester. But for now, it's helpful to just say that thermal energy is really a place to dump excess mechanical energy. Because potential and kinetic both make up what we call mechanical energy, and that's separate from thermal energy. And so we have this simple model here where, in looking at this figure, where a system has different forms of energy associated with it. A kinetic energy, a thermal energy, a potential energy, even this sort of so-called chemical energy. And when energy can be when you can take one form of energy, turn it into another, that's called an energy transformation. So dropping the object from a height, we have the potential transformed into kinetic energy. That's the standard example. But there's many more than that. And so what we want to do in the next few slides is go through several different examples of potential energy, or examples of transformations, rather. So here's the first one. We have putting a shot. I'll offer several more examples besides just this one. So imagine the shot putter. The simplification for this example is that we're throwing an object horizontally. So the system is the shot, and what's the transfer taking place? Now the shot putter, the athlete, exerts a force on the shot. That's work. Whenever you apply a force on an object over a certain change in position, that's what we define as work. And so that work will increase the kinetic energy of the object. It'll make it move. And if you might be wondering, why are we redoing this? I mean, can't we just say that a net force will cause an object to accelerate? Yes and no. You can technically say that, and that is as correct as this new terminology is. Practically speaking, it tends to be more useful in many situations to do work in kinetic energy, because sometimes you don't even know the formula for the force, but you do know the total amount of work. And if you're trying to find final speed, that's buried in the kinetic energy term. If you know the work done, you don't need to know the forces to find the final speed. So it's a way to kind of get around the fact that in many examples, the force is not constant, or oftentimes not even, doesn't have a simple formula. Like the shot putter, I mean, the force that the shot putter applies on the shot is highly variable. It's not a constant force. Well, you can model it as such. But this transformation is what takes place. What are some other examples of this transformation of work to kinetic energy? Other examples that we can think of. One would be kicking a soccer ball. Right? When you kick a soccer ball, it gains kinetic energy by your force applied by your foot. Throwing a baseball, pitching a softball. And actually, the windup, when you think about a softball pitcher, the windup that they do to increase the velocity of it is also an example of work increasing the kinetic energy. The windup and the throw are both examples of work increasing the kinetic energy of the softball. Anything that is launched, anything that changes its velocity in a horizontal direction by an applied force. Pushing a stalled car in neutral, right? You put your car in neutral and you push from the back and it starts to move. That's work to kinetic energy. What are some examples of not, or what are some for which this doesn't apply? Well, orbits would be an example of something that doesn't apply in this situation, because as circular orbits or uniform circular motion, the velocity isn't changing, or the speed isn't changing, and so the kinetic energy stays constant. So even though there's a net force, we can even assign like a little picture to this, right? So you got mass in the middle, object maybe orbiting at constant velocity. That gravity force is not increasing the velocity. It's not increasing the speed. And so this would be an example where there's no change in kinetic energy. So this force actually does no work. It does no work because it's perpendicular to the direction of motion, which we define formally work in a moment. Okay. Anytime we're involving friction and drag, work might not be in place. So yeah, just any of your basic examples of getting an object to move, like hitting a hockey puck, that'd be another example. Okay, playing air hockey, that'd be another example. Pool, right? Playing pool. Not only the cue hitting the ball, not your muscles hitting the cue, right? But the cue ball hitting the other balls. That's all example of work to increase kinetic energy. That's starting example. What about the next example? What do we have? Yeah, pulling a slingshot, stretching a rubber band, stretching a spring, stretching a slinky, sitting down on a cushion. These are all examples of doing work to increase potential energy. Because when you stretch a rubber band, you're doing work. You can feel the force against, and that means you're giving energy to the slingshot or the rubber band. Another example of work to potential energy would be lifting an object off the ground, right? When you lift an object off the ground, just you apply force to it, right? And besides that initial lift where it's at rest, once you actually are lifting it upward, you know, you can assume the velocity is fairly constant. And if the velocity is fairly constant, then how did the potential, so if it goes up, then the potential energy obviously increased. That's because of an amount of work done by this mechanical force. Okay. Lowering the object is a different story because you're doing negative work to lower the potential energy. So yeah, in this example, force is increasing the potential energy. So the work is increasing potential energy by that upward force. Right, you can tell we're always going to be mixing between gravitational potential energy and spring potential energy, or more generally, elastic potential energy. All right, what's the next example? The falling diver. Now, this is the familiar one of an object falling, where you just have potential to kinetic. And this is one that folks often remember from perhaps the first time they've seen physics or something. But yeah, in this example, the object is increasing its speed while it's moving downward. And so you've got the stored potential energy by their height released as kinetic energy of their motion. I think that's pretty clear. This last one, maybe not so much, of a falling meteor. They say a speeding meteor. So again, in all these examples, the system is pretty obvious. And in most cases, it will be. In most cases, the system is pretty obvious. right? But in this case, the meteor, anytime there's thermal energy, okay, we're going to say that we're not talking about heat or anything. We're not going to introduce heat transfer until way into chapter 19. So anytime the thermal energy changes, it's always going to be because of a drag or a friction force, or more generally a dissipative force. So for us, the system in this case, the thermal energy is now shared between the meteor and the air, or for the car braking, the car skidding on its brake to a halt, the thermal energy is shared between the car's tires and the street. You don't really have a way to separate between the two. But sure enough, this would be an example. I don't think this transfer really makes much sense to me of kinetic to thermal, but certainly that kinetic to thermal is the car coming to a halt. What does it say here? The meteor and the air get hot enough to glow. Obviously, it gets hot enough to glow as the meteor's kinetic energy is transformed into thermal energy. Well, where does the kinetic energy go? Oh, I see. This might be re-entry. Okay. So I think in the narrow sense, this would be like a meteor is slowing down as it enters the atmosphere, right? Because meteor's speed before it enters the atmosphere is just getting larger and larger by gravity. And it's kind of the previous example of the potential to kinetic. But once you're in the atmosphere, there's going to be a brief moment where the kinetic energy decreases because now it's in a drag situation, and it's in a drag situation, so its speed will decrease. Continuing though, I mean, the meteor will eventually reach terminal velocity. And so how do you handle terminal velocity? They don't mention it in this slide, but what's the energy transformation for terminal velocity? Well, the velocity stays constant as the object falls. So what is happening here is that it has potential energy that's being converted to thermal energy. So as it enters the atmosphere, sure, its speed will slow down as the thermal energy increases, but the thermal energy will keep increasing as it falls because now the potential energy is being converted to kinetic energy. And if you don't believe me, just go back to a time when you were a kid and you were climbing ropes, and maybe you or maybe your friend would climb to the top of the rope and just slide down, right? What would happen to their hands? That would be rope burn. And that's another example where the friction force increase. So, gravity pulls them down, but the friction between your hands and the rope increased the thermal energy so much that it just split the skin or blisters or whatever. And the rope got kind of hot too, but the rope didn't care. So yeah, that's another example of a transformation of potential to thermal, going at a constant speed. So terminal velocity, even though the potential energy is decreasing, that doesn't necessarily mean the kinetic energies are going up because we have this force. I mean, another example of this situation might be dropping a ball in water. Or if you drop like a metal ball from some height and it enters some tube, some tank of water, right? I mean, it'll have some speed of entry, and then once it's in, the drag forces will lower the speed. So it'll be the same sort of thing, kinetic to thermal. And then it'll settle to the ground as you get potential to thermal. Yeah, in these first examples, we're just trying to go through as many different situations as we can to understand the role of energy, because the problems themselves aren't too hard. It's just sorting out the terminology. Good. Okay, so moving on here, we have what we call the work energy principle. where the energy in the system will change according to the work done by any external forces. So what do I mean by an external force? It's something from the environment. And you have to be kind of careful when you talk about an external force, because whether you include the Earth or not in your system will affect whether or not it is an external force or a form of energy. And so here's the classic picture in the book that I want us to keep in mind when we're doing these energy problems, is that the system has three types of energy. It has kinetic energy associated with its motion, potential energy associated with its location around other significant objects like springs or planets, and it also has a thermal energy. That thermal energy is associated with the microscopic sum of its kinetic and potential energies. If you don't believe me, let me show you real quick an example of internal energy. Go back to the solid example. We'll return to this simulation several times when we do the ideal gases, but a solid, just what we think of as a chunk of a solid, right? These neon atoms, never mind what the temperature is here. I mean, it doesn't matter. But these neon atoms all have an energy associated with them. You see they're kind of moving, kind of vibrating. So they have a certain mechanical energy associated with them. Well, if you add up that mechanical energy associated with every single one of them, that's the thermal energy of the system. So this is a very real form of energy that we're going to be working with. Later in the semester, we'll show how that energy can change when I heat the thing up, and maybe it'll start to melt, or maybe start to evaporate into a gas. It's a fun little thing, but this is not any mechanical way to increase the energy of the system. This is just a thermal transfer of energy. This is heat, where the heat transfer increases the thermal energy of the object. Okay, it's fun to look at right now, but that's not what we're doing in chapter 9. In chapter 9, we're talking about how can we increase the thermal energy of that with mechanical means. So moving back to the slides, there's a quick check question that we'll mention. So yeah, so work is the mechanical transfer of energy by forces. And that transfer of energy, because this is a transfer, going energy into or out of. Work is a transfer of energy. Work is a verb, not a noun. Just like heat is a verb, not a noun. Energy is a noun, right? It is a thing. Work is a transfer of energy. Let's do a quick check question to see if this all makes sense to us. So what are some of these formal definitions, numerical definitions of work and energy? So in this first example where we do work on the system, it's defined as the dot product between the displacement vector and the force vector, right? So in this figure down here, there's a lot of vectors associated with it, so I'm not going to draw them. So this figure on the lower right-hand side here, we have a force applied to a particle with an initial position, and that it may change the speed, it may not, but the speed is irrelevant in this case, because all that matters is that there's a force that had been applied to the object as it goes from position S initial to S final, and that's the displacement delta S. So we define the work done as the dot product of the force times the displacement. Remember, displacement is a vector, and so just like force is, so you take the dot product between the two. We're going to more or less assume familiarity with the dot product. You'll need it probably less than you know of the dot product is what you'll need for these physics problems. And so this is the definition of kinetic energy, like I mentioned earlier. What are the units? It's a joule. The units of work technically are Newton meters, but those are equivalent. And so we got here, we have here the definition of a joule. think it should be capitalized actually. Well, anyway, it doesn't matter, but okay. So let's do a quick check question with kinetic energy to see how we feel about that.